So my name is Joanna Drążkowska. I am currently a postdoc working at the Ludwig Maximilian University of Munich in Germany. And in autumn, I will move to Max Planck Institute for Solar System Research in Göttingen to start my own research group. So the topic today is planet formation. And this will be more like a general level talk, so don't expect like too much detail. I wanted to make it like very accessible for the general scientific public. So let me start with telling you that we know now for a very long time that planet formation is pretty much related to star formation process. So planets form in disks, which are surrounding young stars, which are just being born. And these disks basically form because of the angular momentum conservation. So when a primordial cloud of material, which we call the molecular cloud, is basically just a cloud of mixed gas and dust filling the space between the stars in galaxy, is for some reason disturbed, and it starts to gravitationally collapse. And then this cloud typically initially has some rotation, and thus the angular momentum conservation comes into play. And this basically makes this cloud not to directly collapse to form a star in the center, but some part of this material has to form a disk that is surrounding this star. And in this disk, somehow the planets form. And unfortunately, we cannot really observe the planet formation process per se. So we need to fill the gap in our understanding of this process with some planet formation theory. And this is exactly what I'm working on. So 4.5 billion years ago, from a disk which was surrounding the young sun, which was just being born, the solar system formed. And by 30 years ago, it was the only planetary system that we were sure existed. So that planet formation theory was based basically on explaining the architecture of the solar system, which is quite particular. So in the solar system, we have basically two types of planets. We have the rocky or terrestrial planets closer to the sun. And then we have the asteroid belt, which is dividing the terrestrial planets from the zone of the gas-rich and ice-rich planets. And behind the orbit of Neptune, we have yet another belt of minor bodies, which is called the Kuiper belt. And this is a source of the comets that are sometimes passing by closer to the sun and then experiencing this evaporation-driven activity so that we can observe them. And in so-called classical planet formation theory that was born at in the second half of the 20th century, there was like a big assumption made that these kind of belts of minor bodies, this asteroid belt and the Kuiper belt, are kind of leftovers of the planet formation, and thus we can assume that they sort of represent the initial condition of the planet formation in the solar system. So the assumption was basically that such minor bodies were filling the disk, the protosolar disk that was surrounding the young sun 4.5 billion years ago. So if we look a bit in more detail, the classical theory of planet formation was basically stating that all the dust grains that were filling the disk were somehow very quickly sedimenting to the midplane of this disk and were forming the first gravitationally bound building blocks of planets, which are called the planetesimals, and these are the precursors of asteroids and comets. And then the N-body techniques were used to model the evolution of these planetesimals, And it was found that in such a setup where we basically only have these gravitationally bound, so like kilometer-sized and larger objects, there is a process called the runaway growth, which means that the planetesimals that were born for some reason a little bit larger, they will also grow much faster. And then they will become so-called oligarchs. And the oligarchs, so the largest of them, are kind of winning the race. They will just continue growing by sweeping up the remaining smaller planetesimals. And then those oligarchs that grew large enough, quickly enough, so within the lifetime of this gas in the disk, which is estimated to be a couple million years, then those oligarchs can also start to accrete the gas, which is the hydrogen helium gas, and they gain the gas atmospheres such as Jupiter and Saturn in the solar system. And then the oligarchs that for some reason didn't grow large enough or didn't grow fast enough, so the gas disk already dispersed, then they are just left as the cores of rocky planets, so the Earth-type planets. And the big kind of success or big prediction from this classical theory of planet formation was that the gas-rich planets can only form in the outer parts of this protosolar disk, outside of a so-called water snowline. So the water snowline was this region here, outside of which the ice-rich grains, that are the blue grains here, can exist in its kind of solid form, right? And inside is just water vapor. So basically, there is like a very simple analytical argument that explains why this is such a strong prediction. And this comes from comparing two estimates. One is for the maximum mass of a rocky core that can grow from such a planetesimal disk, which is called the isolation mass. And this is this orange line here. And you can see that this has a big jump, and this is exactly corresponding to this water snowline. So outside of the water snowline, we have much more material available, and also this kind of zone of influence from which oligarchs can gather their material is also increasing with the distance to the central star. So this is why it is easier to form a larger planetary cores when we go outside in the disk. And then we can compare this line to what is the minimum mass of planetary core that we need to start any gas accretion. So what do we need to hold any gas? And this, on contrary, this is decreasing with the distance to the central star. And this is because it is basically easier to accrete very cold gas, so outside of the water snowline, than it would be to accrete the warm gas closer to the star. And this is why this classical theory didn't really predict that the gas-rich planets can exist. One thing that I also have to say here, that this was, yeah, of course, the success, but there were also a lot of problems in this classical theory. And one of the problems was that the time scale for forming these planetary cores was also increasing with the distance to the central star quite drastically, and forming the core of Jupiter, where Jupiter is, so at 5.2 astronomical units, this was taking already longer than the estimated lifetime of the gas in the disk. But since the solar system was the only planetary system, as I said, people were assuming that there might have been some sort of exceptional conditions in the disks that was surrounding the sun, like maybe this disk was having a little bit more of solids that would speed up the growth of solid core, or maybe it was living longer, so that the core of Jupiter could take more time to form and still accrete the gas. But then, of course, the big revolution has happened, and we started to discover the exoplanets, so planets that are orbiting stars other than the sun. And you can see here the graph, which is comparing the planets in the solar system, with their plotted here with the red triangles, in terms of their distance to the central star and in terms of their mass. And all the other dots are the exoplanets that we know to date. And you can see that all of them are pretty much either closer to their central stars or are more massive than the corresponding planets in the solar system would be. And this is just an effect of the observational bias. So the fact that it is easier to detect planets that are massive and planets that are close to their central star, that are just like we can see this interaction better with the methods that we are using to detect these planets. But anyway, we now have good statistics for at least for the planets that we are detecting in large numbers. So we now know that the traditionally first class of exoplanets detected, so the hot Jupiters, very gas-rich planets that are orbiting very closer than Mercury is in the solar system, they are their occurrence rate is roughly 1%, so they surround roughly 1% of the stars in our galaxy. So it shouldn't be such a large, such a big problem to explain them, because they are not so common. But we now know that the kind of a bit smaller planets, but still quite gas-rich planets, which are called the mini Neptunes, they are very common. So they are the most common type of planets in our galaxy, are the ones that are falling exactly in between Earth and Neptune, but kind of close in. And their occurrence rate is estimated to be at 50%. So we really now need a theory that is explaining formation of such gas-rich planets close in, so inside of the snow lines, basically, because there are no stars that would have the snow line at closer than 0.1 AU, basically, right? So this is a big challenge for the classical planet formation theory. But at the same time, there was another revolution that has happened, which is the revolution connected to our observational capabilities in terms of resolving the disks which are surrounding the young stars, the disks that are currently forming planets. And at the end of 2014, the Atacama Large Millimeter Array, so this kind of large-scale interferometer working at millimeter wavelengths, kind of reached its maximum configuration and was able to deliver the first high-resolution image of such a disk, which was surrounding the star HL Tau. And we could see something that we maybe didn't quite expect, that the distribution of this millimeter-sized roughly grains, which ALMA is tracing, is very not homogeneous. So we seem to have regions in these disks, because we now know that this happens in almost all disks that we are able to resolve, is kind of exhibiting these very bright rings and then dark gaps. So it seems that there are some locations in the disk where there is just more of these dust aggregates than in other locations in the disk. And taking all these things together, this forced us, like these developments forced us to revise the classical theory and to focus a bit more on these initial stages of planet formation. So I told you in this classical theory, there was this big kind of jump. There was this assumption that all the dust grains immediately form these gravitationally bound planetesimals. But if we look at all the way from micron-sized dust grains, which are already present in molecular clouds, so we can kind of safely assume that this is really the initial condition for solids in the protoplanetary disks, then the way from micron-sized dust grain to an Earth-sized planet, this covers roughly 40 orders of magnitude in mass. So this is something like 13 orders of magnitude in size. And if we start this story with planetesimals, then we are basically in the log scale, then we are 75% already on the way. So we are skipping a big chunk of what happens. And we now know, thanks to Alma, that these stages are not so obvious, that there is something more going on. There is also the physics, which is changing, because the planetesimals and larger planetary cores are held together by gravity, while the smaller objects, they are held together by cohesion. And this is also a big challenge for planet formation models, that we need to use different methods to model these different stages of planet formation. But to understand better what happens and what are the problems with modeling these early stages, we have to take a step back and we have to look at the structure of such an example protoplanetary disk. So if we want to look at the evolution of a chunk of gas that we choose out of our protoplanetary disk, and we have to look at the balance between three forces. So there is, of course, the gravity between our chunk of gas and the central star, but there is also the centrifugal force, and there is pressure, because the gas is pressure supported, and there is the pressure is higher in the inner part of the disk, which is denser and hotter, and then it decreases with the distance to the central star. And if we make the calculation, we will find out that since this pressure gradient is negative, this means that our chunk of gas is orbiting the star with a velocity which is slightly lower than Keplerian. And this parameter eta measures how subkeplerian this gas is. And this is typically very low number. This is something like 0.5%, but it already has very meaningful consequences for the solid component, because the dust is pressureless, which means that it would like to be on standard Keplerian orbit, but since it is surrounded by the gas molecules, which are slightly sub-Keplerian, it kind of constantly experiences sort of a headwind, and because of aerodynamical drag interaction, it loses its angular momentum and it drifts inwards. And this is called the radial drift. And then the radial drift is just one of the consequences of this interaction between dust grains and gas, but there are more processes. So there is the vertical settling, because the vertical component of gravity from the central object is not compensated by anything. There is the azimuthal drift. So because of this subkeplerian rotation, also the different grain sizes will have slightly different azimuthal velocity. And there is also random components such as Brownian motion and turbulence, because we believe that the protoplanetary disks are to some degree turbulent. And what's interesting is that for all these processes, the dust speed increases with the grain size, which means that different grain sizes again will have different speeds, which will drive the collisions between these grains. And it is extremely important for us to model these collisions, is that we know what happens when dust grains collide at given speed, which we can predict with our protoplanetary disk models. And for this, we have the laboratory experiments. So in laboratories, people try to recreate conditions of protoplanetary disk and create dust aggregates of various sizes, and then collide them with the speeds that we need to tell us what happens. And we have here two examples. One is highlighted is a collision where two small dust aggregates are actually sticking and forming a larger dust aggregate. And then on the right-hand side, we have an example of collisions between two larger aggregates, which are like cylinder-shaped and are rotated by 90 degrees to that their contact point is kind of resembling a sphere. And then you see that they are that nothing happens when they collide; they are bouncing. So there is no more growth. And this is actually the big conclusion that we have. So when we feed this data from laboratories and we build our protoplanetary disk in a computer, so we do dust coagulation models. This is one example that I made with the Monte Carlo type code, where we use representative particle approach. So each dot represents a portion of dust. And then we are kind of looking now at our disk from a side. We start with all our dust grains at micron size. So 10 to minus 4 centimeter is 1 micron. So this is the kind of typical starting point. And then when we let our particles evolve, we can see that they indeed grow. So they change color, which corresponds to larger and larger sizes. They grow more the closer they are to the star, which is also something that we predict analytically, that the collision timescale are shorter in the inner regions of the disk. You can also see that they sediment to the midplane gradually, as expected. And also you can see that with time, we are losing our dust because it is drifting inwards. And then we can look at the very similar model with a different method, just to compare. So now we are using a different approach, the fluid approach. So we assume that our dust is a fluid, which fills now the space again of the distance to the central star on the x-axis, but now we are plotting the size on the y-axis, and we are plotting the density of our dust fluid with colors. So again, this is a very similar setup. We are starting our dust population at micron sizes, so 10 to minus 4 centimeter, and then we are letting the dust evolve. And the effect, like the results that we get, are very similar. So the dust grows faster the closer it is to the central star, and then also it drifts inward. So the conclusion that we have, which is consistent, never mind what method we are using, is that the dust growth is restricted by two things. One of these things is the radial drift, which means that at some point the drift timescale is shorter than the growth timescale, and then the dust is just depleted before it has time to grow. And there is the fragmentation problem. So the dust aggregates collide at increasing velocities, and at some point they just cannot stick anymore. This is what the laboratories experiments have told us. So the problem here is that you see the maximum grain size that we are getting throughout these simulations is something like a couple of centimeters. So there is no way to reach these sizes of gravitationally bound objects, these planetesimals that we need and that we were assuming previously had formed very efficiently. So now, fortunately, we have found a solution for this problem, and the solution is called the streaming instability. So the streaming instability is a two-fluid process in which, again, the dust grains are interacting with the gas, which is subcapillarian, but the dust grains are finding solution to this headwind problem, which is very similar to the solution that the bikers find in Tour de France, for example, where they find that if they clamp, so if they form this kind of peloton, they can deal with the headwind more efficiently, and then they can bike faster. And this is also what our dust aggregates find here, is that if they clamp, so they form these overdense regions, then they can be saved from this radial drift effect. So one important thing is that streaming instability cannot just work in the standard conditions of protoplanetary disk. So it needs the dust grains to grow to larger aggregates, which are called pebbles, and these are the ones that are drifting fast, so are slightly decoupled from the gas disk. But it also needs some initial overdensity. I told you, or I didn't, I already forgot, that the standard conditions in these molecular clouds and protoplanetary disks is that there is roughly 1% solids. So 99% gas and 1% solids. But the streaming instability, in order to efficiently form planetesimals out of these pebbles, needs the dust to gas, so solids to gas ratio to be on the order of unity. So it needs to be really high. And first, like a big development that we had in the last years is that, thanks to the fact that we understood the streaming instability process, we are now able to build models which are connecting dust evolution and planetesimal formation. And we can now make predictions for where the planetesimals form by invoking different processes that are leading first to streaming instability conditions. So here is a plot from my recent review chapter, which is now available on archive, where we are kind of just showing out of the literature what are these things that these results for the planetesimal formation process that people have found in various models. So we have in the right column basically models that are falling closely to this classical paradigm in terms of that they are forming planetesimals. So the blue line is the planetesimal distribution, the gray dashed line is the classical paradigm, which is called the minimum mass solar nebula. And this can be done either by assuming that the solids to gas ratio was increased by a global process such as photoevaporation, which was removing the gas from the disk, or that there were some transient dust traps which were locally making it easier to gather a lot of dust in one place, and that these dust traps were kind of appearing and disappearing all over the disk. And then in the left column, we have outcomes that are more local, so that they are predicting that there are some favorable locations where planetesimal formation is easier. And one of such location, which is now very well studied, is the water snowline. So again, kind of coming back to what was known already in the classical paradigm, that water snowline is sort of a special location, because previously this was the location where our predictions for minimum and maximum planetary embryo was crossing. Now we think this is the location where the first gravitationally bound building blocks of planets can form. And this left column fits more into this new emerging paradigm of planet formation, which I want to talk a bit more about. And this is called the Pebble accretion paradigm. So it was realized that for a planetary core, so this protoplanet, this large black dot that is sitting in the middle of this graph here, it is easier to grow by accreting these centimeter-sized pebbles that are still interacting quite actively with the gas than to accrete planetesimals in this classical paradigm. And this is because the planetesimals are quite easily scattered by gravitational interaction. And even if they at some point are close to our protoplanet, it doesn't mean that they stick around. It may also mean that they are just scattered and they leave this gravitational zone of influence here. But for pebbles, the story is quite different because, as I said, they are interacting quite actively with the gas. The gas is not stopping them immediately, but the gas is slowing them down. And if we are lucky, and for a large chunk of the parameter space, this is the case, that means that the pebbles are slowed down exactly at the time they would nominally need to pass this planet. And that means that they are bound to this planet forever. And they start to slowly settle onto our protoplanet. And this way, the protoplanet gains mass. And another important thing about another benefit of the pebble accretion is that the size of this feeding zone from which our protoplanet can grow is increasing. And this is because, as I said, in this classical paradigm, the protoplanet, so the oligarch, can only accrete from some feeding zone, which is increasing with the distance to the central star, but still it is limited. But for pebble accretion, the story is different because the pebbles are very mobile, and because of this, the protoplanet can just stay where it is and wait for the pebbles to come even from the outer edges of our protoplanetary disk, unless, of course, there is some process that stops them there, like, for example, another planet growing in the outer disk, which would sweep more pebbles. And this pebble accretion paradigm opens a route to forming these very diverse planetary systems, because it is enough to just change this pebble flux, which is incoming to the protoplanet, and we will change the outcome of planet formation. So here again, we have a plot from this review chapter, which is comparing predictions from different planet formation models to the observations. Because if we really want to test our planet formation theory, we cannot just do one model that will produce one planetary system, but we have to run our models many, many times with different initial conditions and then check the statistics of the outcomes. And this is exactly what is done here. This is called the population synthesis approach. And what we are comparing to is this left-hand side panel, which is the observed fraction of stars with different types of exoplanets. And then, as I told you, we are now having a good statistics, so we can bin our planets, and we can also run this through the detection bias prediction. So we know that although we found a lot of hot Jupiters, it's also very easy to find them. So we can estimate that their occurrence rate is something like 1%. Then for warm giant planets, which would be kind of Jupiter analogs, but closer in to the central star, this is about 10%. And then for cold giants, which are the direct analogs of Jupiter and Saturn in the solar system, the occurrence rate is about 6%. And then the most numerous group, or the most popular group of exoplanets, are these super Earths and mini Neptunes with the occurrence rate of roughly 50%. And what's nice is that in many cases we also have information on the properties of the central star for these planetary systems, and then we can also plot with the colors what was the metallicity, so the which corresponds to estimated abundance of solids in the initial protoplanetary disk that formed these exoplanets. And there is a very well-known trend in which we know that the giant planet occurrence scales with the metallicity, so the more metal-rich stars have more gas-rich planets. And then in the middle panel, we have outcome of the Pebble accretion synthesis, which is showing us the outcome of many models done in the Pebble accretion paradigm by Bertram Beach and Michael Lambrecht. And what they did is to create these synthetic disks with various masses, various sizes, various metallicities, and then in each of these disks insert one planetary core which is growing by Pebble accretion and is also migrating inwards, because we also now know that the interaction of the gas disk and the planetary core, so not just the dust, but also planetary cores, are impacted by very different process, by just gravitational interaction, but the outcome is the same. They are moving closer to the central star. And this is why these growth tracks that we can figure out from this plot are also like this, that the planet is growing, but it's also at the same time drifting inwards. And what we can nicely see here is that, again, this scales with the metallicity. So the more dust, the more pebbles we have, the faster our planets grow, and this growth is more competitive with respect to the planet migration. And then for disks with lower metallicity are kind of ending up here more often, so forming a slightly smaller planet. And then from this set of models, we can also estimate the occurrence rates that we would expect, and they are written here. And we can compare them directly to the observations, and we can see that the outcome is actually quite good. And then in the right-hand side panel, we have models made in this classical paradigm, so the planetesimal accretion synthesis by group in Bern. And these outcomes are taken from models from Emsenhuber et al., which are publicly available online. And then we plot here two types of models that they did. One type of models that assumed just one planetary core is growing per disk, and these are the gray dots and the black numbers. And in this case, the occurrence rate of the super Earths is very similar to the Pebble accretion synthesis, but the occurrence rates of the giant planets are much lower. And then we can also check what happens if there are much more planetary cores growing in each disk, and then these cores can interact with each other, and this influences the outcome. And then these are the purple dots and the purple numbers. And in this case, the occurrence rate of the giant planet is better, but the occurrence rate of the super Earth is now very much overestimated. So it seems that Pebble accretion overall gives a better fit to the observed exoplanet population, and that's why it's such an important development. But this is not the whole story. So here I was talking about this period mass relation and also the metallicity trend observed in the exoplanet population. But there is also one more trend which is observed, which is the trend of occurrence rate with the stellar mass. So if we focus on the Kepler mission, which was detecting the close-in planets, mostly these kind of super Earth planets, then there was a very puzzling trend found that the occurrence rate is increasing with the decreasing stellar mass. So smaller stars seem to have more close-in planets, while if we look at a different detection method, which was the radial velocity method, and we extract the data for cold giants, so and again the analogs for Jupiter and Saturn, then there is the opposite trend, I guess more expected trend, that the occurrence rate of this planet is increasing with the stellar mass. So more massive stars have more of these massive planets. And it turned out in the work led by Heismulders that also the Pebble accretion model can explain these trends. And what is happening here is that the giant planets is indeed formed more often in disks that are surrounding more massive stars. And this is just because we know from observations and we assume in these models that the disk mass scales with the stellar mass. So more massive stars have more massive disks, and this is why it is easier for more massive stars to produce these massive giant planets that we assume are sitting at the snowline location. And then we also check what is the possibility of forming a close-in planet. So this is this green line as marked super Earth, because this is kind of analogs for the Kepler planets. And here we find that it also in principle would be easier around more massive stars, but if there is already the giant planet growing, then we have to take into account the effect of filtering, so the effect of just stopping the Pebble drift by this massive planet that is growing in the outer disk. And this decreases the chances of forming our super Earth around more massive stars, and exactly reproducing this trend seen in the Kepler data. And as a bonus, we also make the prediction that if we were able to detect planets around less massive, even less massive stars than the Kepler was focusing on, then we would see reversal of this trend, and we would see that even less massive stars would again produce less super Earths, and this is just because they have less mass available for planet formation. And I think I'm coming to the end of my talk here, and I will show you this overview of this emerging planet formation theory that I was talking about. So we now believe that planets form in this kind of multi-stage process, starting with the dust growth from micron-sized dust grains to ever larger dust aggregates until they reach the size of pebbles. So the pebbles is the stage where our dust aggregates are decoupling from the gas in the disks. They are colliding at higher and higher speeds, and because of that they cannot grow any farther than a couple centimeters, but they are useful for forming planetesimals in the process of streaming instability, which puts us directly into the gravitationally bound object stage. So it's planetesimals, kilometer sized and larger. And then these planetesimals can grow in this traditional runaway and oligarchic growth, but then the growth of massive planetary cores of the mass of Ceres and higher is greatly sped up with the Pebble accretion process, which again uses the same pebbles. So we have to be careful. The mass budget is now becoming very important. And the big question is, how much mass do we really use for forming our planetesimals, and how much mass is left from these pebbles to speed up the growth of planetary cores. And then a nice thing is that the Pebble accretion can, in most cases, lead directly into the gas accretion phase. So there is no need for the giant impact phase, which was previously needed because the oligars couldn't grow as large. And there are also these two red boxes which mark where these radial redistribution processes are becoming important. So one of the processes is the radial drift of pebbles, and the other is the migration of planetary cores. And what I need to stress here is that we are actually still lacking fully self-consistent models that would be starting with dust and going all the way to the massive planets. So typically, even the Pebble accretion models would start with already planetary core already formed, which is able to accrete pebbles. So this is something that we are working on very intensely. So still a lot of work left to do, but I believe that we made great progress in the last years in understanding the planet formation process and in coming closer to understanding the formation of the solar system and the diversity of exoplanets within sort of one unified picture. So I just leave you with a couple of takeaway points, and I'm happy to take any questions.
Okay, thank you, Joanna. Very nice talk. I enjoy a lot. I'm working on physical properties of asteroids and trans-Neptunians. So all this knowledge of formation of solar system is very interesting for me. I have a couple of questions. One was related with the kind of a star that each planetary system are. So as I understand, our sun is a third generation star. So it's formed from after 2 or 3 supernova that produce the material that form the sun. In all the simulations, you take into account that the composition of your initial material is solar type, but then you show a plot, very nice, when you show the difference between the metallicity of the star. So what happened if the planetary system is forming around a 2nd generation star or a 4th generation star? I don't know. It's very important, the relation between gas and dust. So you need to have dust.
Yeah, indeed. Is I think it's a big mystery on when the first planets could form. So currently, actually, the oldest exoplanet hosting star that we know, I think, is about 10 billion years of age, which is, so it is more than twice older than the sun. But obviously, probably it wasn't really the star that formed from hydrogen and helium only. So there already had to be some dust at that point. And this is indeed a very important parameter that is sometimes the whole planet formation process, right? It seems to be, there is some minimum threshold of the solid that we need. And the big question is what this threshold is, and how planet formation proceeds around stars of extremely low metallicity. I don't know, we have very good answers. One possible answer is that planet formation could proceed with completely different routes, so not with this core accretion paradigm that I presented here, which assumes that there is the solid core of the planet that is formed, and then it is accreting a gas. But there is also the gravitational instability paradigm, which proposes that the whole protoplanetary disk is gravitationally unstable, and it can fragment. So it can parts of this protoplanetary disk can collapse directly to gravitationally bound objects. The problem is that for these to happen, the disk needs to be very, very massive, and it needs to cool very quickly, which is actually, I think, easier when there is more dust. So I'm not sure how well this works, but it is a possibility.
Thank you. My second question, if I allow, is about the migration in our solar system. The migration is very important because you first form Jupiter and Saturn, and then Jupiter migrate in. But when the Jupiter migrates out, this is very important point for the formation of terrestrial planet. And the key point there is the existence of Saturn. So it's your second gas giant there. So what is the paper of migration? Because you need to have the second planet to stop the first one to migrate to create in our case at least, our terrestrial planets.
Yeah, in fact, so as I said, for example, in these kind of models, we make this big assumption that there is only one planetary core per system, right? And modeling migration of multiple massive planets is a big challenge because it seems to be quite hard to find universal prescription. Like migration of one planetary core is quite easy to insert into these type of models, but migration of multiple planets requires to make a full-scale hydrodynamic disk model plus n-body interactions between these planets, and these are completely different models. That's why I think the formation of the solar system is, of course, much better studied, and we are able, because we have so many constraints, we are able to make such a detailed models and spend a lot of computational time on modeling this one system. But these kind of models are much more general level, right? So you need to run so many of them that you cannot spend a lot of time on each single one. So in fact, I think before we find some sort of a universal, easy analytical prescription, I think we are, we cannot really fully answer this question of how important this kind of process is for exoplanets.
So maybe we can say that we have no super Earth here because we have the migration and we have a smaller sizes terrestrial planet due to the migration.
Yeah, I think this is the view currently, as far as I understand, is that we don't have super Earth in the solar system because Jupiter formed early enough to stop the solids that would be incoming, right, as the Pebble flux from the outer disk. So the inner part of the solar system was sort of shielded from too many solids coming at it.
Okay, thank you very much. I will read your paper, your review. Thank you.
Thanks.
I have another one. Old problem is that connection between the grain, very small grains, and the pebbles and the kilometer-sized objects. So thinking in the same way that the material that form our solar system is a second or third generation, they form from a cloud that is a consequence of the explosion or of something, a supernova or whatever. What happens if the grains are not so small in that cloud and the starting point is larger? So you don't need the problem because your grains are larger than the micron sizes or millimeter sizes. So you start from a meter or kilometer sizes.
Yeah, then the problem would be that we would lose them very quickly. If we start with meter sizes, then they are at the peak of this radial drift problem. And then we lose the population of solids in the matter of probably thousands or tens of thousands years. So it is actually not quite helping in this in that sense. But yeah, there is definitely this kind of ongoing discussion on the initial sizes that we have in the molecular cloud.
In some works recently, they use fractal shapes in the dust, so they can go for larger sizes at the initial.
Yeah, the fractal has the advantage that they have different surface area to mass ratio. So they have a slightly different aerodynamic drag interaction. And then this helps to fight this radial drift problem because they stick more easily. But as far as I know, in the end, they always fall into the same pitfalls, like the radial drift timescale at some point becomes faster than the growth timescale, or these fractal grains are also maybe not so stable in terms of high-speed collisions with smaller aggregates that are then destroying them. So as far as I know, it's still the streaming instability hypothesis kind of wins in a sense.
Okay, thank you.
Okay, so I think Giuseppe typed in some questions, so I may try to answer also. So first is Pebble accretion synthesis does predict a population of unobserved cold Earth. Yes, but as I said, we cannot observe them because of observational bias. So basically, that's the line that you can see here where the points end. It doesn't mean that there are no planets. It just means that we have no knowledge, right, of these planets. So with the future exoplanet finding programs, possibly we could detect more planets also in this part of parameter space, and then we could put some numbers on the occurrence rates that we could then compare. But for now, we just have no knowledge on whether these planets exist and how numerous they are. And then other was, if you form enough hot Jupiters in situ, there is no room for migration. So as far as I understand, I'm not an expert in the gas accretion models, but gas accretion is still very hard for the hot gas. So still the planets start accreting gas when they are still in the outer disk, and then they are moved inwards because of migration, and that's the dominant story for hot Jupiters. And then there is 30-year-old works on possibility of concentrating dust at the center of vortices formed due to gas turbulence. This is actually still ongoing work, because there are still new pieces emerging to the story as the computational models for modeling the interaction between gas and dust in 2D and 3D models are improving, because we need quite a lot of computational power to do this. And as far as I know, there is no consensus on whether the feedback from the dust that is gathered in the center of such a vortex is then not destroying this vortex. But definitely the vortices and in general the hydrodynamic instabilities are still a very, very hot topic on whether, yeah, they can help us with forming planets.
Can I make a last question?
Sure.
What about the free-floating planets, the isolated planets? How we can imagine them? I mean, they form it isolated, or they are ejected?
No, I think the dominant the dominant idea is that they are ejected. So this is something that happens after the stages that I was discussing. So basically, the planet migration seems to be leaving the systems quite compact. So basically packing the planets together typically in resonances. And this is stable as long as the gas disk is around. But then when the gas disk disperses, these systems very often turn unstable. And it seems that very often one or more planets is ejected from planetary systems, like these very young planetary systems that just were left without the gas that was stabilizing their orbits. And yeah, there is even some possibility that this happened even in the solar system, that the solar system started with 5 giant planets, and one of them was lost during the Nice instability, which is currently the dominant model for explaining the architecture of the solar system. But yeah, this is something that happens kind of after the stages that I am mostly interested in.
Okay, yeah, because I listened a talk by a researcher in Vienna, in Austria, about these free-floating planets, and she said only 10–15% of the that planets are ejected. The other one are formed in the cloud.
Interesting. Yeah, I was not aware of this.
And they took a spectra and was very similar to a brown dwarf. But it's really hard to imagine what is the composition of this planet without a star.
I would assume if it's a process that is similar to star formation, just at less massive fragment of a cloud, then maybe it's just a substellar object, which is averaged molecular cloud composition, but somehow didn't ignite the nuclear reactions in the middle.
Correct.